Thank you. So as mentioned, my name is Roy Hassan, Business Development Manager for Amazon Athena. Today's session, we're going to do a deep dive into best practices for using Amazon Athena. So from the agenda perspective, we'll go through a number of things. We'll review the previous year, what we've done, the new features that we've been developing, some of the use cases that we've seen our customers use during launch or after launch. Talk a little bit about Athena and Redshift Spectrum and EMR and how they integrate together. Connecting with Amazon Athena, a number of different ways to do that. Creating tables, Glue Data Catalog, partitioning, and some of the other best practices for query performance optimization. So we launched Amazon Athena back in November 2016. Since then, we've introduced a number of functionality and capabilities across the board based on what our customers have been asking for and what we've seen from usage around in the field. The first one that we've introduced is REST-based APIs with support for a number of different AWS SDKs in the supported languages such as JavaScript, Java, Go, etc. The other piece that we introduced is CloudTrail support. So for auditing queries that your users are submitting, you can actually look them up in CloudTrail and be able to get the statistics of what is going on with those queries and how they're behaving. In addition to that, we also introduced JDBC and ODBC drivers, and that gives the user much more flexibility in choice of tools to be able to interface with Athena. We launched in 11 AWS regions across the globe, added support for Avro and Geospatial Data, and also querying using Grok expressions. So those are regular expressions that you can use, so you have more flexibility with the type of data that you want to query with Athena. We support also encrypted data using S3 server-side encryption and also customer supplied encryption, as long as those keys are available in KMS. We've built integration with AWS Glue, particularly the Glue Data Catalog, and we'll talk later about what that integration looks like and how you can take advantage of it. CloudFormation support is also available for named queries. So if you wanted to build infrastructure and include specific named queries defined in that infrastructure, so later users can just simply call those queries and execute them on the fly, you can build that out inside of CloudFormation. Like I said, CloudTrail will be able to audit all your application, all your queries via CloudTrail. We also recently announced support to launch an Athena table directly from the CloudTrail console. So that's another really easy way to look at your CloudTrail logs. Also integration with S3 Inventory and EC2 System Manager. Really nice features that are recently introduced. Allow you to query S3 Inventory logs and your EC2 System Manager logs directly in Athena. Since our launch in 2016, we've added many customers. Many of you are probably listening to this webcast today. We want to kind of thank you for all that. We've learned a lot from our customers, many of the use cases we've thought about, but also we've come across a number of new use cases that we didn't really think about, didn't really plan for, but it's really nice to see the adoption of Athena and the different use cases that our customers have been using Athena for. In addition to our customers, we also have introduced several integrations with a number of partners around the BI. So this is tied to our JDBC and ODBC support. Partners like Tableau and MicroStrategies and Qlik. There's also other ones that we've recently announced with Looker and Domo. Also Amazon QuickSight. So a really great way to visualize and explore and interface with your Athena data. So you may have heard of data lakes. It's a concept of making all your data available in a single, highly distributed, highly available data store on AWS, such as Amazon S3. So the idea here is that there's a number of ways that you can get the data in. You may have the data sitting in data warehouses, in on-prem databases, but you want to bring that data into a data lake, right, into Amazon S3, because we have to make sure that there's a way for the different organizations or the different users within the organization to bring their own tool, their own interface to work with that data. So not everybody wants to use SQL. Some folks want to use some machine learning tools to build models, use Amazon EMR using Spark or Hive or Presto on top of that. Having the ability to access that data directly in S3 makes it extremely available and scalable for organizations to explore and innovate. Another use case that we've seen is embedding SQL capabilities inside of your application. So when you look at an application that has been developed, you have the application on the left side making API requests to the infrastructure, but instead of being backed by a database, being backed by an Athena table and data sitting in S3. So if you do need to have a lower latency, maybe hot data, you can have that data sitting in an RDS database for quick access. The majority of the data resides in S3, so it gives you a much more scalable and cost-effective solution to be able to serve your application. So one example of that is Timber.io. So Timber.io is a new startup that has built a service that aggregates logs and enriches those logs in a number of different ways and makes those logs available back to the user in an easy-to-use interface. So if we look at their architecture, it's a pretty simple architecture. The bottom part of the architecture shows the log ingestion process, where they're ingesting the different logs, they're doing some transformations, they're converting it to a columnar ORC file format, then they're storing it in a partitioned manner on S3. And we'll talk about what partitioning means a little bit later on. They're using the Glue Data Catalog to update the partition information, the metadata for that data, which then makes that available from a query interface to Athena. Now, to make it easier for their users, they don't necessarily expose a SQL interface to the users directly. They built a front-end API that allows them to take the request that the customers wanted to do and then split it up into a number of different SQL queries that are then issued to Athena in the background. Data is retrieved and returned back to the user in an easy-to-use or easy-to-consume manner. So that's a very simple application that kind of shows you the power of using Athena and a backend to interface with a front-end user interface that's more appealing to your users. Another common use case that we're seeing is migration from an on-prem infrastructure to the cloud. So on the on-prem side, whether that's a database, whether that's Hadoop environments or a data warehouse, there's a number of different capabilities that those platforms provide. Capabilities like ETL for data transformations, data wrangling, machine learning, interactive querying, and some data science applications. But a lot of it is kind of revolves around this Hive metastore, right? The metadata layer that gives us a representation of the data and where the data actually lives. So if we look at how that data translates over to an AWS cloud environment, there's a number of different tools and capabilities that allows you to take these use cases or these tasks that users have previously done and break them out into their own individual best tools for the job, right? So rather than having a Hadoop on-prem environment that does all of these things on the left, we now introduce a number of different tools that makes the job easier. So if we look, for example, for ETL, we have Glue, which is a serverless ETL environment. But if you wanted more flexibility and more optimizations, you can actually use EMR to do the same kind of job, but have furthermore control over the capabilities, the applications, and the optimizations that you can do to the infrastructure. Similarly, for data wrangling and interactive querying, many times in a data science or BI environment, you can use Athena, you can use EMR, or even Redshift for any kind of any of those workloads, right? Depending on how you want to interface with it, whether it's an ad hoc interactive manner where Athena will be a great choice, but maybe you have some complex data warehouse type of reports, or Redshift will be a better choice for that. For machine learning processes, EMR provides a number of different tools from Spark, Spark ML, and other machine learning libraries that are built and distributed on that infrastructure for machine learning. And then lastly, from a meta store perspective, the Glue Data Catalog ties all of these components together. So instead of managing the metadata or the location of the tables in a number of different places, we have one place that manages all of that, and then all the tools that we mentioned, Glue, Athena, EMR, Redshift, basically points to that data catalog and is able to discover and explore that data from a single place. So another example of a data lake is then once you have the applications on the left side where you have databases on-prem, data warehouses, maybe even streaming application coming in, the connection here is that data comes in and we have these crawlers that you see here in the AWS Glue crawler component that is able to extract the schema and infer the schema and the type information from these different data sources and populate the data catalog. So then that middle layer of data catalog is then available to Athena, EMR, Redshift Spectrum to be able to point to that and say, I want to be able to query this data without them individually having to own that metadata and being managed in a siloed manner. Now everything is managed in a centralized, fully distributed, and fully integrated manner, making it very easy and accessible for different teams and different organizations to bring in their own tools for the job that they need to accomplish. Another example is querying logs. It's very common to see organizations leverage the AWS service logs such as CloudShare logs, ELB logs, VPC flow logs, etc., and be able to try to extract some relevant information regarding troubleshooting or service activity, but many times even billing, right? So you can look at the billing reports and understand better how your services are billed on AWS. So to do that, a simple workflow would be to take these service logs and write them into an S3 bucket, and all the AWS service log give you that option of exporting the data into S3. We then use a simple Lambda function that will update the data catalog to say, hey, new data has arrived in these buckets, make that available for Athena. And then from within Athena, you can write a simple SQL command that will look up that data and give you the results that you're looking for. And if we take that a step further, we can actually use Glue ETL to look at that raw service logs and do some kind of transformations. Maybe we want to clean it up. Maybe we want to enrich it with some additional data. Also, we want to take that raw data and convert it to a columnar format that is more performant for Athena to query. So when you have a lot of this data, and many of our customers have terabytes and terabytes of service logs, take that data and convert it to a columnar format, reduces the amount of data that you end up saving on S3, but also increases the speed of the performance that Athena can return the query results. And that also results in lower cost on Athena usage. So there's a lot of value here to including Glue ETL in the pipeline. So you told us that there's a lot of different service logs, AWS service logs. So why do you need to really go out there and create these tables and build these pipelines? There needs to be a better way, a cleaner way. So the way we've been approaching this is providing a number of different architectures and solutions via the AWS Big Data Blog. So if you're not familiar with it, go online, check out the AWS Big Data Blog. There's a lot of very interesting blogs there. But what you'll see is that we've basically taken some of these common service logs and provided very easy to use data pipelines of how to set that up so you can make it available for querying in a very simple way. As an example of that, we have querying and visualizing the cost and usage report. So if you want to look at your billing information inside of Athena and also visualize it with QuickSight, there's a very easy to use and easy to follow blog that allows you to do that. Similarly, how do we take DynamoDB objects and kind of do a top-end analysis on that using Athena? Also be able to build a serverless architecture for analyzing CloudFront data, right? How do I want to look at the different bots that are accessing my web infrastructure and be able to categorize them? So here's a nice way to do that. You can also audit Aurora database logs. So database logs are stored to S3. You can write simple SQL queries in Athena to audit those logs and make sure that everything is operating as expected. Just another one, looking at VPC flow logs using Kinesis Firehose and Athena and QuickSight, right? Another way to look at the infrastructure, be able to troubleshoot it and make sure that everything is operating as you expect. So again, go back to the AWS Big Data Blog. There's a number of blogs. We're adding them on a regular basis. A lot of really interesting use cases and examples of how to use Athena and some of our other big data products to build interesting data pipelines. Another great example is Airbnb StreamAlert. So StreamAlert is an open source product that was released by Airbnb for the purpose of streamlining log aggregation, log mining, and reporting in the infrastructure. And typically this is used with security teams or DevOps teams to be able to monitor their infrastructure and report and analyze any type of events that are happening. So it's completely serverless infrastructure, very easy to set up and to get started. Supports many different environments, so cloud, data center, if you have any on-prem environment. Supports different types of data, so as data comes in from your applications, whether it's JSON, CSV, key value pairs, even syslogs, as your application exposes that information, the StreamAlert system is able to consume that, process that, and make it available for you to trigger alarms based on a set of rules that you define. So here's an example of a StreamAlert architecture on AWS. So on the left side, you have a number of different data producers writing data in a streaming manner to Kinesis, or maybe in a batch manner to S3. And then that data is fed into a rules engine where you define and classify the rules that you want to apply to that data. So as the data comes in, you can say, if this is a particular event, does it meet a specific security classification, and then that data can then be pushed to some kind of notification entity like PagerDuty or Slack. But as those events are going through the system, we're also saving them into S3, so you can use Athena for historical search and analysis on all those events happening. So here's just one simple example of how Athena is being used in StreamAlert. So as objects are landing in S3 from a number of different sources, there's a notification that is sent to an SQS queue. That SQS queue then triggers a Lambda function. The Lambda function takes that sets of data, may move it to a different bucket, updates the data catalog in Athena, so it's aware of that new data that's coming in, and then Athena is available to query that data. So a very simple way that Athena is being used in a StreamAlert system, but also gives you a really nice serverless and cost-effective way of searching through the historical events that are happening through your environment. Another use case that is very common, and specifically we're seeing this in enterprises, where enterprises have a number of different databases or data stores that are holding a lot of archival data or historical data that are there for the purpose of auditing or some kind of retrieval at some point, but are not really hot data. It's not something that actively is being searched or used. So it makes a lot of sense to take that data and move it to a more cost-effective storage location on S3. So we use a service such as AWS Database Migration Service that will replicate these tables from these databases onto S3. Once the data lands into S3, we can trigger a Lambda function to be able to update the data catalog and make that data queryable via Athena. So instead of keeping it in a costly data stores for no reason, move it to S3, very cost effective. And then when you do need to access that data, when you do need to query it or audit it, it's very easy to do it using Athena. Another example that we're seeing more and more with customers is more around time series data, and this comes from real-time events being generated by mobile application, by IoT devices, whatever it may be, pushing those events, those real-time events through a Kinesis firehose, and then that data lands in S3 in a partitioned way. Then we have either a Lambda function. We can also substitute AWS Glue in here if you wanted to convert the data or enrich it in some way, update the data catalog, and then that data becomes available for Athena again to query. So not just can you query historical data, but you can also query real-time data coming in to S3 using Athena. So that's a really nice way that we've seen more and more of our customers interfacing with Athena. Geospatial data is another set of functionality that we've added recently. We're seeing more and more of the usage pick up for geospatial data as customers hold longitude and latitude information, but be able to take these geometric shapes and be able to create them inside of your data set and be able to search across a geometry. Makes it very easy when working with geospatial data. So we talked a lot about S3 as being sort of the base of that data lake. We talked about also the data catalog being that central layer of metadata information. And the real reason for that is to be able to give you the option to pick the right tool for the job. And as you see here, the storage layer is still S3, but we have the option to use Amazon Redshift Spectrum, Amazon EMR, or Amazon Athena to be able to query all that same data without having to move it or replicate it in any way. So they give you a choice of the right tool. So if you have analysts, for example, that need to do some ad hoc interactive querying, they can do that via Athena. But you may also have data scientists that also need to access that same exact data for some machine learning processes. So they can also access the same data without really having to worry about competing for resources with other folks. They pick the right tool, they use the data in place without replicating it, without duplicating it, or without really worrying about any kind of compete of resources with other folks. So there's a number of ways to connect with Amazon Athena. When we first launched, it was available in the console only, so you can open up the console, you can type in SQL commands in the console and get access to the data. But since then, we've introduced JDBC and ODBC drivers. That opens up the door for a lot of different tools to be connected to it. As I mentioned previously, we have a number of BI partners, such as Tableau and Looker and Domo, that are available to query Athena, but also the APIs. APIs are extremely powerful when you're automating the interaction with Athena. You've seen previously how Airbnb, StreamAlert, and Timber.io's services are interfacing with Athena, and they're all interfacing via the API. So that's a very nice and simple way to interface with Athena and build it into your application. So here's just an example of how Amazon Athena can be used via the API. This is an asynchronous API. We have an API that says start query execution. You pass in a simple SQL select statement. You tell it where do you want to save the output of that, whether there's any encryption involved in it, and then you let the query go. Once the query completes, you can then call the get query results API, passing it the query execution ID and also a pagination. Say I want to say how many results do I want to get back, and then you'll get those results back from your SDK and be able to process that. Very simple to use. So creating tables and databases. So I mentioned a lot about data catalog. So those are all about the DDL. So DDL is the definition language that we use to create tables, to modify tables, to modify the partitions and things like that. So there's a number of ways to do that in Athena. You can use Hive DDL statements. So if you are familiar with Hive, those are create external table statements that you can pass in the table name, the column names, and a bunch of other properties and create those tables in Athena. You can also use the Athena API to pass those similar DDL statements to Athena if you want to automate it. You can also use it via the JDBC and ODBC drivers. However, as we look at Glue, and we'll talk a little bit about that later on, Glue provides a couple other ways to do it. So one way is these crawlers, and crawlers are an automated process that allows you to define a target S3 bucket that the crawler will go out and inspect that bucket and infer the schema and extract all the schema information, the table information, and create the table for you without really having to worry about creating DDL statements or anything like that. So it's really an automated process to discover the data and populate the data catalog. In addition to that, you can use the Glue APIs to create the tables themselves. And that simplifies the process, gives you slightly better performance when it comes to a large number of table creation or table modification operations. So if you are in a region where Glue is also available, as well as Athena, using the Glue Data Catalog for the API to update and modify your table information is much more efficient and much more recommended. So here's just an example of what a table looks like. Now you notice here that we're saying create external table. In Athena, that's one important concept to remember. All the tables are referred to as external tables. And what that means is that the metadata, the table definition, and the physical table, the physical data are completely separated. So what we're doing here is we're simply defining the metadata for that table. We're defining the table name, the columns, the type of data, where the data is going to reside, but we're not necessarily touching the physical data. So for example, if I was to delete this table, this metadata will go away, but the physical data will remain. So that allows us to create a number of different table permutations on top of the same data without really affecting the actual data. So in this example here, you can see that we're defining an external table. We're defining a couple of the columns. We're also saying what type it is, right? This is a text file and it's delimited by a tab. And we're also pointing a specific location to an S3 path. And that tells us where the objects are on S3. So when we're scanning the data, we know exactly where to find them. So that brings us to the differences between schema on read versus schema on write. So schema on write is typically what you see in databases and data warehouses, where you sort of define the schema and you create the schema in advance of that data. So you create that schema and then you load that data into that table that has to match that schema. And there's benefits to that, because once the data gets pushed into that schema, you can do some kind of verification to say if the data doesn't quite fit the schema, we can drop that row, or we can modify, or we can do some checks around it. But it's also very restrictive in a sense that once I have the data defined, the schema defined, I can't really change it anymore, right? It is what it is, and the data fits it, and that's good. But we can't really have a lot of flexibility with that. So when we look at the schema on read, on the other hand, it basically says that I'm going to define the schema when I read the data. So not when I create the data, but when I read it. So that gives us some flexibility around accessing and reading the data in a number of different ways. So for example, if I have a table that has, let's say 100 columns in it, I, as a user, may say, I only care about the first 10 columns. So I can create a schema still backed by the same data set that only represents 10 columns. Then another user comes around and says, you know what, but I really care about 50 columns that are not the same as the original 10. So I'm going to create my own schema, only listing those 50 columns that I care about, still pointing to the same table. So now we have two different schemas representing the same data set. So that's kind of the flexibility that we have with schema on read. The SerDes and SerDes are serializers, deserializers. Those are basically processes that we use within Athena to process or to extract the relevant rows from different file types. So regular expression, grok is basically a named regular expression pattern, very easy, very easy to use when you have log data, when you have structured text. So you can kind of define regular expression patterns for different parts of the text and group them together in these grok expressions, make them very easily reusable across a number of different applications. JSON, OpenCSV, TSV for tab separated, and then into columnar formats like Parquet and ORC, Avro and Geospatial are also supported. Now I'll leave the compression formats to you to sort of explore, but there's a number of different compression capabilities as well. It is important to note that when Athena reads the data and when Athena charges you for the data that you scan, we charge you on the exact data scan, which means that if your data is compressed, we will only charge you for the compressed data. We're not going to charge for the uncompressed data. So it's very important to make sure that your data is compressed. Also make sure to use the suggested compression algorithms for the particular file formats. For example, Parquet and ORC have suggested file compression algorithms, but do not compress the actual file itself. Let the engine compress the individual blocks inside of these files. All right, so what is the data catalog? So we talk a lot about the AWS Glue Data Catalog. Think of it as this unified metadata repository across a number of different data stores. So these data stores may be Amazon RDS, relational databases, Redshift, S3. It may also be relational databases on EC2 or even on-prem, right? So that gives you a single place, a single view into all of your data. So you have the ability to search and explore and discover and share with your organization the different data stores, the different data sets that are available throughout the organization. That makes it very easy to start implementing data lakes and really exposing the data that's available inside the organization to everybody in the team. So back to this slide again. We've seen this a few times already, but this is a common architecture for a data lake, where again we have all of our data stores on the left side. We bring that data in. The crawlers can then crawl all of these data stores and create the metadata in the data catalog. So as I said, this is the central kind of Hive compatible meta store. Now the applications on the right side, Athena, EMR, Redshift Spectrum, they're now able to call the data catalog and say, I want to get access to table users. I want to get access to table credit cards, right? Without really knowing where the data lives or anything else, they simply go into the data catalog and they say, I want this table. And behind the scenes, everything will be connected, making it a very seamless solution for accessing data across a large data lake. So what do you have to do to set this up? So when you look at the Glue Data Catalog console, you can see that in this example in particular, there's a number of different tables. Each one of these tables belong to different databases. But when we look at the classification, we see that there's a number of different classifications here, right? There's CSV, there's Redshift, there's Postgres, there's Parquet. So this again tells you that all of these data sets are available for you to explore and to use, and they all come from different data sources. So when we run the crawlers or we create these tables in Athena via the DDL statements, there's a lot of different information that's available for you in the data catalog. So we provide table properties, there's some data statistics. So as the crawler infers this data, it also tries to count how many objects, how many files are available, how many rows are available in all those files. This information becomes very useful as you crawl this data periodically, and as the data evolves over time, you can actually go back in time and see previous versions or previous runs of my crawler. What did the data look like, and did anything change? And you can actually keep track of that. So we do version those schemas. So as any schema changes happen, somebody adds a row, adds a column, deletes a column, modifies a type. That information is captured in the data catalog as a version, giving you the option to compare versions and also revert back to an older version in case that's the version that is the most accurate. The other really nice thing is we talked about these partitioning, these partitions, and these partitions are really useful when we're dividing the data up in S3 to make it easily accessible from a query engine, but also very efficient. So as we have these partitions, when we select a set of data, we're able to go into the particular partition and only extract the data relevant to that partition instead of trying to scan the entire data set. So for example, if we say, select all the users that were born in month of April, the query will only run to the April folder and be able to pull only the data from that folder, not have to scan everything else. So that reduces the amount of data scanned, increases the speed of the performance of the query, and also reduces the cost of that query because we're not scanning as much data. The beauty of the crawlers is that they can actually automatically detect these partitions and create these partitions for you in the data catalog, but even more importantly, they can actually keep it updated. So as you add new partitions, as new partitions get added over time, the crawlers can periodically run, find those partitions and create those partitions in the data catalog, keeping your metadata up to date and relevant. So what are crawlers? So crawlers are a simple application that can be configured to talk to an S3 location or to a JDBC connection, such as a database. We can have some built-in classifiers. So if there's certain classifications that we do not currently support, such as JSON, CSV, Parquet, etc., you can bring in a regular expression and you can say, okay, this file is a text file. I know how I'm going to parse this. Here's a regular expression pattern that allows us to parse this and extract column information and type information and be able to create a table out of that unstructured data. Once the data is extracted, we then put it into the data catalog, make it available for all the other tools to consume. All right, so when we talk about classification, classifier can really recognize the schema and the types of that data. So as we look through the data in S3 or even in a database, we try to match the schemas that we detect from each one of the files or each one of the data sets, and we try to see, is there any match between that schema? So when we classify it, we say, okay, is all of this data JSON data, yes or no? Then we go through each one of the files and we say, does the schema look the same? Is the schema very similar to the previous file that we inspected? If the schema is very similar, we treat it as the same table. If there's slight modification or slight changes in that schema, that could imply a schema evolution where a new field was added or a new column was added. We will then try to merge that schema up to give you a superset of all the different schemas for that set. Now, if there's a much greater difference between that schema, we will then say, okay, that is a different schema. We're going to create a separate table out of it, and that allows you to kind of crawl through a large number of files and break them out in ways that either they're completely different tables or maybe some of them are related to other files, and we're going to kind of bunch them together in one table. So that's a really nice way to automate some of the data discovery. Even though your data may not be properly partitioned or properly organized on S3, you can use the crawler to sort of build that organization for you in the data catalog. So as I mentioned before, we kind of go through and how do we detect these partitions? We go through the folder itself in S3, and we go through and we identify those partitions as we see them. And there's in this case, in this particular case, we're talking about Hive compatible partitioning, where you have the column name equals the value of that column. We can identify that, and we can then see based on heuristics that when we look at all these folders in S3, they have a common structure, naming convention, and we can then identify that those are partitions, and we extract that information and we build those partitions in the data catalog. But if you really want to write your own classifier, and I mentioned this previously, you can use regular expression, and this grok pattern is common in a lot of places, but basically it takes regular expression and it gives it a name. So you create a name, a regular expression, and then these names can be reused in a number of different ways. So in this example here, we're taking a timestamp and some message prefixes, and we're using them to extract relevant columns out of our unstructured log data. So when we talked about the data catalog, previously when we first started, when Athena launched and Glue Data Catalog was not quite yet available, Athena used its own data catalog. Now, behind the scenes, all the DDL requests, all the create table statements, the alter partition statements, everything arrived at the Athena web service. We converted those DDL statements into API calls, and we called the Athena data catalog to store that metadata. But as Glue became available, we then switched that model around and say, instead of calling the Athena specific data catalog, we're going to call the Glue data catalog. Now, this is only available where Glue, in the regions that Glue is available. In the regions where Glue is not available, we're still using the Athena data catalog there. So when you're moving from the Athena data catalog to the Glue data catalog, there's a simple process to do that migration. Now, there's some modifications that you have to do to the existing Athena policies in IAM. There's a name policy there, so you can use it and basically assign the right Glue data catalog permissions to Athena to use. We also wanted to add one layer of protection, so you don't necessarily give access to anybody to migrate that the data catalog from Athena to the Glue Data Catalog. So we introduced this additional permission that the administrator will have to include in their account, so they can actually then have the permission to say, yes, go ahead and update my data catalog, rather than allowing anybody to click the button and say migrate data catalog. So that's just a protection that we've added. So when you're ready to do that migration, that basically add this IAM policy to your admin role, and you'll be able to migrate your data catalog. The benefits of upgrading to the data catalog, to the Glue one, again, you have the ability to then share that metadata across a number of different tools: EMR running Hive, Spark, and Presto, Athena, and also Redshift Spectrum. You can also use the Glue API to directly update and modify schema information, partition information. We have many customers that are using this to pre-populate partitions in advance, also modify the partitions. That gives you higher concurrency and also better performance when dealing with metadata management. You can also use the crawlers, as I mentioned previously, to automatically discover the metadata and also keep your partitions up to date. And then you can also leverage the Glue to actually ETL the data, and this is a very common use case where data comes in a non-optimized text-based format, using the Glue ETL engine to then take that data, convert it to a columnar format such as Parquet or ORC, and make that available for Athena to query in a much more performant way. So we talked a lot about partitioning, and partitioning is actually a very important concept, and it's pretty simple to actually implement. And the real reason for partitioning is because we want to have this separation of the data files in a number of different columns. And when we separate those data files, like I showed previously, a very common one is to use year, month, and day, where all the files relevant to a particular year, particular month, and day exist in one folder, while subsequent month, years, and days are available in other folders. So when you're scanning the data and you say select star from table where year equals 2017 and month equals December, we will only go to those folders and grab the files from that folder. Now, it doesn't necessarily need to be time-based. We support any columns. So if you wanted to have a user ID or a category or a group, that's all possible. Very easy to set up. So time-based or date-based is not the only way to do it. Again, the real reason here, what we want to do is because we want to reduce the amount of data we scan, and that results in faster completion time of queries. Also reduces the query cost. So we're scanning less data, you're therefore paying for less of that data. There's a number of ways to define these partitions. The crawlers can help you define those partitions. DDLs can be used to alter partitions and to add partitions. You can define those partitions as the table is being created, but you can also define them in advance. So once the table is created and new data is added, you can say, for example, I'm going to create my partitions for tomorrow. So I don't have to automatically add them as they come in. I can sort of pre-create them in advance. So many times that's an interesting use case, and it's very helpful for customers. So this is just a good example to do. So here's an example of a couple of different queries that we run on non-partition tables and also partition tables. So if you look at the first one, it's a simple count from a data set that's about 74 gigabytes, and we're only looking for the count of a particular date. So when we run it on a non-partitioned table, it takes about 9.7 seconds to complete, and it scans the full 74 gigabytes of data. Now, when we look at a partition table, it actually takes us 2 seconds, and we scan a whole lot less data. We scan 29 megabytes of data. So it's significantly cheaper and faster to run it on a partition table. The second query does kind of the same thing, but shows you how you can do the scan over a range of dates. And again, if we do this on a non-partition table, it takes about 10 seconds to complete. We still got to scan the entire table because it's not partitioned. So we have to go through each individual file in that table and look to see if those dates are available in that file. But if we go to a partition table, we don't have to do that, right? We're scanning a lot less data. more than the previous query because we're scanning through a range of dates, but still took about 2.7 seconds to complete, and we only scanned 871 megabytes as compared to 74 gigabytes. But there is an overhead. So partitioning is a double-edged sword. You don't want to over-partition and you don't want to under-partition. So if you do over-partition, there's still a penalty for us to be able to go through the partition information in the data catalog and prune out the partitions that we don't need and only read the ones that we do need. So if you look at this example here, when I'm doing just a simple count, on a non-partition table, it takes 8 seconds, still reading 74 gigabytes of data, but on partition table, since we're not really using the partitions here, we still have to go through and prune those partitions out. So it took a slightly longer time to complete that query. So definitely take that into consideration. Having a lot of partition is not a good thing, but there's definitely ways to address that. So when we talk about these partitions, what do they actually look like from a table metadata perspective? So when we're creating a table, you can see that the table definition is in front of you, and then we add this extra piece called partitioned by, and here we define what we want to partition this table by, so the year and the month. And if we look at that on the bottom, this location path basically says this is the base URL for where to find the data. The year part of the partition refers to the first portion of that path. And then the second portion of that path is the month partition. And after that comes the files themselves. So if we look at this example, it shows you where the base path is in blue, and then the year is the column name that we're going to use the partition, and then the value, the 2017, and then month is the next partition name, and then 11 is the month. The actual value of the month. And underneath that, that's where all the physical data files will reside. There's another way that I didn't really talk about to sort of update partitions, and this is this MSCK repair table. So this command can be executed in Athena, and what that does is it goes through all of the partitions available from this base path, and it goes one by one, and it says, is this a partition? Let me add it into the table. So if you have a lot of partitions, this operation is going to take a little bit of time. So definitely take this into consideration. But if you have a new table with a little bit of partitions, this is a good way to sort of rebuild those partitions and get started. But once you've done that once, then you can use the command above that says alter table, add partition. That's when you manually add these partitions. Of course, you can use the Glue API. You can also use the Glue crawlers to automate a lot of this process and keep your partitions up to date. All right, so the partitioning that I showed you previously, that's also known as Hive partitioning. And the reason it's called Hive is because when Hive does partitioning, it creates the column name equals then the column value. But you also see many times, particularly in Kinesis or in Kafka or in other tools, where partitioning does not necessarily have the column name in it. It just has the value. So in this case, you can see we have the table path, and then we have just the number 2017 and the number 11. In our partition by clause in a create table statement, the first element represents the first element in the path. The second element or partition represents the second element in the path. So year is the first one, month is the second one. So it's really position-based as opposed to name-based. So again, MSCK repair table in this case does not work, because when we run MSCK repair table, it goes through the path and it says, find me the column name and the column value. But because we don't really have a column name here in the path, MSCK repair table is not going to work. So you can use the regular, add table, alter table, add partition method, also the Glue APIs, and also the Glue crawlers will work in this environment as well. So loading it. So here's just an example of how these partitions can be loaded. So like I said before, MSCK repair table will use the Hive-based partitioning. We load all of these partitions into your data catalog. Another way to do it is just using simply alter table, add partition, and you can add those partitions manually. And the real value here too is you can control the partitions that are being added. You can control when they're added. So if there's a certain amount of data that exists already on S3, but you don't want to actually make it accessible or queryable to your users, you can just not add those partitions. So once you feel comfortable that the data is ready for that user to be querying it, then you can add that partition into the data catalog. So that's another way of sort of moving things around and then making data available whenever you think it's the right time. Another example here is when you're trying to match the S3 best practices for high performance and availability by adding the hash value after the path, you can actually incorporate in here, and then you can use the auto table add partition method to pass that path in, and then allow you to create these partitions off of that. So that gives you the ability to match the Hive best practices with the S3 best practices into a method that allows you to have high concurrency on S3, but also still benefit from partitioning that in your query. So like I said before, there's a number of ways of loading partitions. Lambda via Lambda function, you can add those via the APIs, and I showed many use cases where that's the case. MSCK repair table, you can do that. It is expensive operation on a lot of partitions, so definitely keep that in mind. Auto table add partition is a good way to do it. You can also batch partitions up to 99 partitions at the same time. So if you are to use this, you can do it. More preferred is the Glue Data Catalog APIs. Again, it's high concurrency, much easier tool to use. You can automate it very easily with the rest of your infrastructure. So definitely, if Glue is available in your region, definitely take a look at that as one good option to manage your partitions. And of course, the crawlers, if you wanted to simply automate the partition detection, if you're not doing anything out of the ordinary there, then you can use the crawlers to automate that process. So when you choose your partitions, right, there's, the columns can be used or any number of columns. Now, before you go out and say, I'm just going to create partitions, it's going to be based on the date, take a step back and think, how are my users going to query that data, right? Are their users really going to be querying the data and filtering based on a time, or are they going to be filtering based on maybe a user ID, right? So taking a step back and thinking about how is the user going to be querying this is going to allow you to pick the right columns or the right partitioning that you want to have on S3. So if, for example, the user is never going to use date, they're only going to use, let's say, customer ID. If you partition based on date, those partitions will never be used. So now you've created the overhead of additional partitions. We have to scan those partitions from the data catalog, but you're not actually using it because you're not pruning any data, so you're not really getting the benefit. So think hard and well about what the partitions need to look like. And again, it's very important to come at it from the user perspective, understand really how they're going to consume the data, what is the methods, and what are the ways that they want to look at that data. Okay, so the last kind of portion of this webinar that I want to talk about was just more around query performance. And there's a number of different things that you can do, and this is not a complete list. We do have a blog post on the Big Data blog that talks about some of the top performance tricks and tips that you can use for Athena. So I definitely recommend going on the AWS Big Data blog and looking at that blog post. But here's just a few of them. So a common one is, the common problem that we see is the small file problem. And this is a problem across the board for big data tools, where having a lot of little small files is very hard to process because of a lot of network round trip, a lot of connections being open and closed, files being open and closed. There's just a lot of management overhead to achieve that. But as much as we want it all to be in large files, there's a lot of small file systems out there, right? Kinesis, Kafka, log outputs. We want to get the data out as quickly as possible. Therefore, we're ending up creating a bunch of small little files. But if we can't do it, and if there is an option via some ETL or some compaction process to take all of these files at some point in time and compact them together into lesser but bigger files, there's definitely a significant speed up from doing that. And of course, converting to columnar formats, again, makes a big difference there. So the reason we kind of talk about this is, like I mentioned before, there's a lot of streaming data coming in. A very common use case is log aggregation. So you may have, application logs, service logs, IoT device logs, all coming in a streaming manner through Kinesis, Firehose, and all those files are very small files, and they just land in S3 because you want the near real-time process. You want the near real-time sort of logging of the data into S3. But if you were to go and query that, it's not very performant. So what we need to do is we need to take that and we need to build these aggregations, and we kind of call them compaction, where you take these little files and you compact them together into larger files, making them available in another bucket. Now, Athena is a great SQL tool, so you can basically say, I'm going to create one table that points to the smaller, more near real-time data, but only a portion of it, right? Only the last 24 hours, for example. And I'm going to create another table that represents the historical data that's already been compacted and converted. So now I have a fast data and I have a slightly slower, older, colder data. Within Athena, I can then union those two tables together and get a view of the fast and the cold data together in one dashboard. So that's a very common approach that we're seeing around log aggregations, really when you want to get that, that near real-time view, but also still have the ability to go back in time and look at your data. So we talked about columnar file formats, ORC and Parquet. Based which one to pick, that's a good question. Many times, customers have to kind of do their own testing to kind of figure out which file format meets their data better and their query patterns better. But the bottom line here is that you want to go from text-based formats to columnar-based formats for the reasons that this table is showing, where in the first line here we have a text file, around 1 terabytes of data. To query that took us 236 seconds, and we scanned the entire data set. So that cost us the full amount of $5. But if we do this in Parquet, in columnar format, we're only, the size of that file compressed significantly. So the columnar format, just the fact that the data is structured in a columnar manner, allows us to compress that data in a very efficient way. And on top of that, we add additional compression, such as Snappy or gzip, that compresses the entire set even further. So to go from 1.15 terabytes of data to 130 gigabytes, significantly cost savings on S3, but also from a query perspective, when we're querying that data, it takes us much, much quicker to query it, and we're scanning a lot less data because we can be much more intelligent about which columns we need and what bytes we want to grab out of that file instead of scanning the entire thing. So they went from paying $5 for that first query to paying a fraction of that for Parquet. So there's significant amount of savings from an S3 storage perspective, data scan perspective, and also the total cost of the query. Another thing to look at is when you typically do order by operations, it's very important to kind of set a limit on that, because many times when order by operations are used is because you want to know what is the top 10 users or what are the top 100 websites visited. So there's really no need to let that query scan the entire data set. If you're saying limited to 100 or limited to 10, we'll go out, we'll get the results, and we'll return only those 10. So reduces the amount of data that has to be scanned and also the time it takes that query to complete. Joins, so join performance is actually a very important aspect. One key to remember here is that when you're joining tables, typically you join a very large table and a small table, such as a fact table and some dimension table. Having the larger table on the left side and the smaller one on the right side improves that join performance significantly, as you can see here by these results. So again, something to keep in mind when you're doing joins in your queries. Regular expression is a very common way to do searching inside of your SQL queries. Now, Athena behind the scenes is able to take those regular expressions and compile them into a much optimal machine code that can be executed on the environment in a very performant way. So when comparing regular expression to SQL operations such as like, you get significant performance improvements, you can see here, from simply using the regular expression function, the regexp like function, without having to use the like operation. So again, if you want to shave or at least gain some performance, this is another way to do that. And that's it. I'll stop here and say thank you very much for your time. Hopefully you learned something, and looking forward to using Athena a little more. Thank you.